Hi guys, क्या हाल चाल है भाई? How are you guys doing? Hello everybody. Good morning, good morning. कैसे हो आप लोग? It's good to see you after almost 4-5 days. Yeah, 4-5 days. I guess my last class was on Wednesday, and then I fell sick. Thursday, Friday I couldn't take classes. Saturday, Sunday usually classes तो होती नहीं. So it's lovely to see you guys in the morning once again, and I'm fine. I'm doing good. I had a bit of fever and associated whatever issues. Okay, and so my son actually fell sick, and so then everybody started falling sick in the house, and so somehow like even if it is a minor viral fever, so it just gets spread from one person in the family to other person in the family. Yes, so lovely to see you guys over here, and I hope you guys are doing good, and happy Dashera to all of you. If I'm not wrong, a lot of places are celebrating Dashera today, though according to the calendar it's somehow started yesterday, but a lot of people are celebrating Dashera today. So happy Dashera to you guys, and I hope this year brings you all the happiness and all in the world to you, and may all your dreams get fulfilled, like whatever you desire get fulfilled. So keep yourselves healthy, keep yourselves nice, keep yourself hydrated, study hard, and don't worry about a lot of things. Okay, chalo. So let's start today's session, and let's start today's session with the first thing, that is discussion of the last class's problem. If you remember, I had given you a problem that what is the number of nodal planes in a dz square orbital. A dz square orbital. So this orbital that you are seeing in front of you, one is a three-dimensional representation, like a static representation. One is like a more vivid representation of a d or z square orbital. So what you were supposed to tell me in the comment section is that whether the dz square orbital has any nodal planes or not, and if there are nodal planes, then how many nodal planes are there. So a lot of people did answer. I'm sorry to disappoint a lot of you guys, is that most of you have answered incorrectly. The answer is, see, what you guys do is you consider that the angular nodes are located on, if you look at it, they are located on nodal planes. Okay, they're located on nodal plane. So what you do is you take the azimuthal quantum number. So the azimuthal quantum number for this is 2, and so you will say that the nodal plane is 2. However, this answer is incorrect. The given orbital does not have any nodal plane, so there are no nodal planes. Okay, there are no nodal planes. Please do remember that the dz square orbital has no nodal planes. Now, what is a nodal plane? It's an imaginary plane which passes through the origin and does not bisect the given orbital at any point. So you take any imaginary plane, pass it through the origin at any angle, and it should not bisect the orbital at any point. Now, is it possible that I can draw a plane and it does not bisect the orbital? Like if I draw a plane present in the xz axis, yz axis, or xy axis, if the plane is present in any of these two axes, then it is gonna bisect the orbital at some other point. Okay, so there is absolutely no plane which is present which does not bisect it at any point. So what is present? So the important thing to note over here, and this is pretty interesting, that what is present over here is rather than a nodal plane, is a conical nodal surface. Like the ice cream cone that you see, the ice cream cone that you might have seen is the one which is present. So this is the ice cream cone. This is the ice cream cone. So there are two conical nodal surfaces. Okay, this is a nodal surface. Okay, this is a conical nodal surface. So conical nodal surfaces, can you see? So if you take two ice cream cones and you join them endwise, okay, you take two ice cream cones and join them endwise, within the ice cream cone is the dz square orbital. Okay, within the ice cream cone. So if I take an ice cream cone like this, and if I take another cone like this, within the cone is the lobe of dz square orbital. So please do remember that the dz square orbital does not contain a nodal plane, because nodal plane should be an imaginary plane passing through the origin, which bisects the orbital at no points, which, or we can say it does not bisect the orbital at any point. There is no such plane present. What is present are two conical nodal surfaces. So angular nodes are present on, they are present on two conical nodal surfaces. Okay, the middle portion is a donut, a reduced region of electron density present around present on the xy plane. Okay, sure. So I hope you have understood this, and there was only one person who had like given almost decent level of answer. So angular node, Shubhajit Mandal has given the answer that the nodal plane is equal to L. Nodal planes is 2 in dz square, which I find is wrong, but he has given a statement which like almost like going in the right direction. There are two conical nodal cones instead of a nodal plane. There is no perfect nodal plane, and Shubhajit is from West Bengal, Bankura. Very good. I have a friend from Bankura. One of my juniors. He is currently in Yale. He's doing his postdoctoral fellowship from Yale, and so many juniors of mine are from Bankura. There is a Bankura Christian College, if I remember. It's a very good chemistry department. Anyways, good to see that at least one person has given the answer. Chalo. So I hope you have understood this. I hope you have understood this. Okay? Chaliye. So before I go ahead, I have a small announcement, and it's just like a small promotional announcement. Why this promotional announcement after so many days is because all the good work that we try to do on the Facebook, it has to be supported in some other way. If some students take subscriptions, then it gets balanced out. So there is a NEET and JEE Pro subscription which has a very decent offer, that is that you can avail up to a 50% discount, maximum of like 12,000 rupees of off, if you use the if for the on these dates, so 24th, 25th and 26th, and if you use the coupon code, that is SRV Pro. There's a description in the box which is given. And so, and yes, Risha, you can leave, no problem. Okay, so the thing is, why this? Because all good work has to be supported somewhere. And there are, see, on YouTube we do discuss a lot of things. However, the complete detailing of things does not happen because of the limited time, as well as one another factor is that we cannot have a very good one-to-one interaction. So if you are interested in that one-to-one interaction, then what you can do is you can go for the pro subscription. Okay, the pro subscription gives you access to all the live courses, and all the topics are covered in detail. You can take the course that you want. You can take courses taught by me, you can take courses taught by some other teachers, you can take courses taught by somebody, Vani ma'am, or someone who is teaching biology, as well as for JEE. And it's just like a subscription. It's like a Netflix subscription. You take the subscription and you just avail all the benefits that comes along with it, and you can avail classes in English as well as in Hindi. One of the major differences between the online session, when the YouTube session and these sessions, is that there is a huge amount of in-class doubt solving. Over here we can attend to only limited number of doubts for a limited period, but over there the class durations are longer, almost 2 hours of class, and you can chat with the teacher, you can interact with the teacher, and all the benefits, I guess you know most of the benefits. But the most important point is, like, why go for a pro subscription? Because if you want to cement your understanding even further, you can go for pro subscription. Also, taking the subscription helps us do all the free work that we try to do, all the work that we try to do on YouTube more and more efficiently. Okay, someone has to support it from some other end. Anyways, so that was all about this. And so guys, please do remember that if you want to avail that 50% discount, if your any friends want to avail that 50% discount, they can go for the coupon code that is the SRVPRO. SRVPRO, that is SRV for Saurav, PRO. Okay, just do let me know that if you have any queries, you can just drop a mail at saurav.goswami@vedantu.com. If you have any questions about this, saurav.goswami@vedantu.com. And so I'll help you like clarify a bit of your doubts regarding like what is the course gonna offer, and if you are having any confusions, you can just drop me a mail. Okay, chalo. So let's start today's discussion, and let's start with a question. Okay, the question is this: if the delta naught of the crystal field stabilization energy of a ligand and the pairing energy required for electron pairing in an orbital is P, okay, then ligand is called weak ligand or weak field ligand if weak field ligand if. What do you think is the right answer? I'm good, Kunal, thank you. So if delta naught of crystal field stabilization energy, I had told you what is delta naught. Delta naught is the extent to which the orbitals are split. Okay, delta naught is the extent to which the orbitals are split. Delta naught is the extent to which the orbitals have a difference in their respective energies because of the repulsions between the ligand electrons and the d orbital electrons. And pairing energy is the amount of energy that you are investing in pairing the electron. So what is the meaning of a weak field ligand, which is applicable for a weak field ligand? So what is a weak field ligand? A weak field ligand will involve or will ensure that electrons remain in the unpaired form rather than getting paired. So pairing energy should be more than the splitting energy, and so for that reason, okay, the right answer is B. Okay, the right answer is B. So is that clear? So the right answer is B. If anybody wants to revise, so this is the 8th lecture of coordination compounds. We have discussed all of these things in the previous lecture. If anybody has a query regarding what is delta naught, what is pairing energy, please refer to the previous lectures. If you come today to attend these, then you will find it difficult, because these things, the basics for these things have already been discussed. Okay, the basics for these things have already been discussed. So chalo, let's go ahead. Let's go to the second question. The second question is this: the CFSC delta naught for a metal in D7 configuration in presence of a strong field ligand is. How do we answer this question? Okay, how do we answer this question? So CFSC, so how do you calculate CFSC? So CFSC is calculated like this. If you want to calculate CFSC, CFSC will be calculated as, so CFSC is calculated as the difference of energies in a crystal field environment compared to a non-ligand field environment. Okay, so energy difference in presence of ligand minus energy in absence of ligand. This year in JEE mains as well, they had given a question about crystal field stabilization energy. So CFSC delta naught, how do we calculate? Now in presence of a ligand, how do we calculate it? In presence of a ligand, please do remember it's octahedral. So unless and until anything is given, I guess it is supposed to be an octahedral field. Okay, so for octahedral field, what we have to do is we will use the formula minus 0.4 delta naught times number of electrons in T2G plus 0.6 delta naught times number of electrons in EG, okay, plus whatever number of times the electron gets paired. So if I take a D7 configuration, it would be written like this. If it is in a strong field, it will be written, the configuration will be T2G6 EG1. Okay, the configuration will be T2G6 EG1. If you recall T2G6 EG1, then it will be written as minus, so number of electrons in T2G will turn out to be minus 2.4. Number of electrons is 6. This will be 6. This will be 1. And so minus 2.4 delta naught plus 0.6 delta naught. This will be giving me how much? Minus 2.4, 0.6. This will be minus 1.8 delta naught. Okay, minus 1.8 delta naught. Okay, so if it is minus 1.8 delta naught, then what is the, how many times the electrons is getting paired? I have to add that as well to it. So the electrons is getting paired 3 times, because if I write the T2G6 configuration, then it has to be paired 3 times. Okay, so this is in the presence of a ligand. But when there is no ligand, then D7 will be written like this: 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay, so there will be, it will be something like this. Just a moment. This will be the arrangement in case of a D7 configuration. Okay, this will be the arrangement in case of a D7 configuration. So you can see that it is being paired twice. So what I will do is I will subtract. So the energy, what is the energy invested when there is no ligand? The energy invested is only in pairing the electrons. So that will be 2p. So ligand turns out to be minus 1.8 delta naught plus 3p and subtract 2p. Our answer will turn out to be minus 1.8 delta naught plus p. The closest match is D. However, none of the answers are completely correct. This should have minus 1.8 delta naught plus p in it. Okay? Is that clear? Okay, so Pahul sir, guys, see, Pahul sir was supposed to come by today. I'm sure that he is on his way, and he went for a vacation. So he'll update you guys that on the channel that when he is coming back. Okay, so he was supposed to come by today, but you know how travel timings are. Sometimes you get delayed, sometimes you come early, and don't worry about it. Okay, Pahul sir will be here, I'm pretty sure, by today evening or tomorrow. Okay, so I guess that he'll be here by today evening or tomorrow, because he is on a vacation and has taken a vacation after such a very long time. So give him some time, guys. Okay, chalo. So our answer should turn out to be minus 1.8 delta naught plus p. Clear? Chalo. Let's go on to the next question. The crystal field destabilization for high energy D4 octahedral complex. So the moment you say high spin D4, high spin means we are using a weak field ligand. The moment I say that it is weak field, or whenever we say high spin means weak field, because when we take high spin, the spin multiplicity increases. So if I have a D4 configuration which is high spin, then the configuration of the complex, the metal atom in the complex, will turn out to be T2G3 EG1. Okay, it will be T2G3 EG1. If it is T2G3 and EG1, then please do remember what is the formula that I gave for calculating CFSC. So CFSC is the energy in presence of ligand minus energy in absence of ligand. Now energy in presence of ligand will be written as T2G3, so minus 0.4 delta naught times 3 plus 0.6 delta naught times 1. And is the electron undergoing pairing? D4 configuration high spin, there is no pairing, so no pairing energy will be added to it. And absence of a ligand, in absence of a ligand, D4 configuration will be in this form: 1, 2, 3, 4. So it will be 1, 2, 3, 4. This will be the arrangement. So there is no pairing at all. So finally, so this will be 0 and this will be, so it will turn out to be minus 1.2 plus 0.6. So it will be minus 0.6 delta naught. The right answer should turn out to be D, minus 0.6 delta naught. Okay, the right answer is minus 0.6 delta naught. Okay, I hope you have understood the question and you have understood how to solve questions like these. Is that clear? So minus 0.6 delta naught. हमेशा याद रखो that whenever you are taking the CFSC, CFSC is stabilization. So stabilization means with respect to something. So if I am saying that I am getting more, I am becoming happier, or I am happier by having my lunch today, that means I'm comparing it with yesterday or some other day. Some other day I might have had some chapati or something. Today I've had something like puri chole, something like that, and I'm happier. Okay, so I have compared my happiness. So every these feature like stabilization, happiness, sadness, all of these are like comparative measurements. So you need to make a comparative. So there is a comparison, and what is the comparison? If there are ligands, what is the energy versus when there are no ligands? That is the comparison set. Okay, so that is the comparison when there are ligands versus when there are no ligands. So when there are no ligands, how do you make that assessment? You just draw the configuration and see how many times the electrons are getting paired. When there are ligands, then check whether it is a weak field ligand or a strong field ligand. According to that, write the configuration and then identify how does it go forward. Okay, so is that understood? That how do we have to approach this problem? Please do remember that a lot of places this approach is not being taught, and a lot of places the approach is being just given to you guys to just it's written that you have to memorize it like that. Okay, I've told you like how does this actually turn out to be. So please do follow it. Okay, even in this year JEE mains there was a question from CFSC and they had used exactly the same concept to solve the question. So easy 4 marks, otherwise -1. Okay, so let's move ahead. Let's look at this question. According to the crystal field theory, the 5d orbitals of an octahedral complex is split to give. This is a very easy one. What do you think would be the right answer? 2 orbitals of low energy and 3 orbitals of higher energy. 3 orbitals of lower energy and 2 orbitals of higher energy. This should be 2 TWO, not TO. 1 orbital of lower and 4 of higher. 4 of lower and 1 of higher. What do you think is the right answer? 2 orbitals with lower energy and 3 with higher energy. 3 with lower energy and 2 with higher energy. What do you think will be the right answer? Very good, Gurjot. Very good, Bhanu Prakash. The right answer will be B. Okay, the right answer will be B. So there will be 3 orbitals of lower energy, that will be the T2G set, and there will be 2 orbitals of higher energy, which will be the EG set. Okay, and so the right answer turns out to be B. Clear? Chalo. Let's move on to the next case. In case of high spin situation, in which condition do we have high spin? In which condition do we have high spin? Please try to identify it from these representations. When do we have a high spin situation? Do we have a high spin situation when a delta naught is greater than P, equal to P, or delta naught times or lesser than P, or delta naught times P is equal to 1? What do you think will be the right answer? In case of a high spin situation, what do you think will be the right answer? Very good, Akanksha. The right answer should turn out to be C. Very good, very good. The right answer will be this. High spin means weak field, and low spin means strong field. Okay, low spin means a strong field. So that is how we answer the question. So if it is weak field, it will be written as delta naught is less than P, and it will be delta naught which is more than P. Okay, I hope you have understood this. So I've already explained you how to calculate CFSC, so we'll skip this slide and let's go on to the next question. For an octahedral complex, which of the following d electron configuration will have the maximum value of CFSC? P signifies Saurav Bhattacharya is asking that what does P signify? So P signifies pairing energy. So pairing energy is the amount of energy that you have to invest to put two electrons in the same orbital. So you have to put some energy because both of them are carrying negative charge. So there must be some energy invested so that these electrons stay in a given orbital. That energy is known as P. So for an octahedral complex, which of the following d electron configuration will give maximum CFSC? Where would we be having maximum CFSC? So maximum CFSC will be obtained when what do you think will be the right answer? So high spin D6. High spin D6 means the configuration will be T2G. So 3, 4, 5, 6. So T2G4 EG2. Low spin D5 means T2G5 EG0. This will be T2G4 and this will be T2G5 EG2. Okay, now if I have to calculate this, the method is pretty simple. If I have to just look at the maximum value of CFSC, I just need to look at the magnitude. Okay, I just need to look at the magnitude. So high spin D6, this will be how much? So for A, I would write this thing as minus 0.4 times 4 delta naught plus 2 plus 0.6 times 2 delta naught. So that will give me how much? Minus 1.6 plus 1.2, that is minus 0.4 delta naught. Okay. B option will give me T2G5, that will be minus 0.4 delta naught times 5 plus 0.6 times 0 delta naught, 0.6 delta naught times. So this will turn out to be minus 2 delta naught. C option T2G4. So this, if I put 4 over here, this will turn out to be minus 1.6 delta naught, and D option will be T2G5 EG2. T2G5 means minus 2 delta naught plus EG2. So plus 1.2 delta naught, that is minus 0.8 delta naught. The magnitude, the maximum value is obtained for B. So the right answer will turn out to be B. Yes. Obviously, only magnitude is taken. So it's just like resonance energy. So CFS, resonance energy, is also exothermic. So you look at only the magnitude. Okay, you do not look at the sign of it. From the sign, you just try to understand that whether it is becoming more stable or is becoming less stable. So if it is minus something, that means that some energy has to be given out while it is forming a complex. And how much energy is given out? Corresponding to 2 delta naught. Okay, so the right answer should turn out to be B. Yeah, the right answer should turn out to be B. I hope you have understood this. Okay. Very good. Very good, Akanksha. Very good, Tejaswini. Very good, Gurjot. Very good, Murlidhar. Okay. A low spin D6 cation in octahedral field will have the following energy. Please tell me, what do you think will be the most appropriate choice? Lowest spin D6 cation in an octahedral field. So again, CFSC has to be calculated. For lowest spin, the moment I say lowest spin, what does it mean? Lowest spin means strong field ligand has been utilized over there. We have utilized a strong field ligand. So if I utilize a strong field ligand, what can I say? It is minus 0.4 delta naught times 6. So D6 will be written as T2G6 EG0. So plus 0.6 delta naught times 0. And how many times it is getting paired? How many times the electrons are getting paired? The number of times electrons are getting paired over here is 3. So I will write 3p. And this is the energy in presence of a ligand field. Okay. Minus, what is the energy which is invested when there is no ligand? So D6 configuration would be written as like this. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So minus P. So I would write this thing as minus 2.4 delta naught plus 2P. The right answer, minus 2.4 delta naught. Actually, this should have been the closest. This should have been 2P. If this is 2P, then it will turn out to be the right answer. Okay. Okay, or if this turns out to be 2p, then it would be the right answer. Options are not very correct. I'm sorry for that. Options are not very correct. The right answer will turn out to be could be either B or A, but you need to have this 2p term over here. You need to have 2p term over here. So either B or A, but 2p term should have been there. It cannot have so the answer will turn out to be none. In fact, the answer will turn out to be none. Looking at the options, we need to change. If I change the options and I make it 2p or make this 2p, then it could be either A or B. Okay. Now none of them is the answer. Okay. So at times you come across questions in which none of the options match your work. Many a times you feel that your work is incorrect and you take it on yourself to just match the answer. Don't do that. Have confidence on your efforts, have confidence on your learning, and whatever you have learned until now, if is correct, you will always get the right answer. Options can always be incorrect. Okay, there can always be incorrect answers. Okay, options are completely wrong over here. Option should have been minus 2.4 delta naught plus 2p. Clear? Chalo. With this, let's move on to the next part, which is known as the tetrahedral complex. So let me just explain this to you. And this is a pretty interesting thing to understand. What is a tetrahedral complex? Since you have understood octahedral complex easily, it should not take you a lot of time to understand tetrahedral complex. tetrahedron. What is a tetrahedron? In a tetrahedron, if you take a cube, okay, if you take a cube, a tetrahedron can be represented like this. So suppose you take a cube, a tetrahedron will be represented in a manner that the central atom is sitting over here and the ligands are approaching from alternate corners. Okay, they are approaching from alternate corners. Can you see these corners? Or you can say that non-adjacent corners. These are the corners from where ligands are approaching. And tetrahedral means there are 4 ligands. So, okay, there are 4 ligands. So, if the metal if the X, Y and Z axes are projecting from the metal like this, if the metal is present at the origin and this is Z and this is X and this is Y, then none of the ligands are present on the axes. Okay, so in a tetrahedral complex, the ligand approach through between the axes. This is what you can see over here as well. They're approaching from between the axes. They're approaching from between the axes. So since the approach from between the axes, they do not lie in the path of any d orbital. In fact, they do not lie in the path of any d orbital. However, mathematically we can prove that the angle between them and dxy, dyz and dxz is less compared to, so if I have to write this, you can do this mathematical calculation. So the angle between ligand and dxy, dxz, dyz is, let me just write this in a much better way. Angle between is less than angle between ligand and dx square minus y square and dz square. So if the ligands are approaching the orbitals at a smaller angle, then the repulsions will be more. Okay, please try and understand. If the approach of ligands and the orbitals are taking place at a smaller angle, then the repulsions will be more. So if the angles are less, then repulsion will be more. So non-axial orbitals are directly between the axes and experience more repulsion. It is because the angles between these non-axial orbitals and the ligands are more and they are raised in energy, while dx square minus y square are lowered in their respective energies. It is different from octahedral field, because in octahedral field what was happening is that the d orbitals which are present along the axes, their energies were increasing and the others, their energy was decreasing. But over here, the orbitals which are present between the axes, their energy is increasing compared to the, so exactly ulta ho jayega. It will just be opposite. So the splitting was taking place with 3 orbitals in the lower energy and 2 orbitals in the higher energy in octahedral. But if it is tetrahedral, it will be the opposite. Okay, it will be the opposite. So this is how it looks like. Can you see this? So there are 5d orbitals and you can see that these 5d orbitals have split into 3d orbitals which are lying in a higher energy set and 2 d orbitals which are lying in a lower energy set. Okay, exactly opposite of octahedral. And please do remember that the energy difference between them is given as delta T. It is no longer given as delta naught. Okay, please do remember that the energy difference between them is given as delta T, not as delta naught. Delta T represents splitting in tetrahedral field. Okay, crystal field splitting in tetrahedral field. So delta T is crystal field splitting in tetrahedral field. Okay, and please do remember two very important points. Science world, I am good, thank you. Okay, please do remember two important points. Number of ligands in tetrahedral is less than number of ligands in octahedral field. Okay, and second point is approach is not in the same. So approach in tetrahedral is not along any d orbital. Okay, approach, yeah, we can do that. Sanjay Shukla, very good question. Can we relate? So this is what I will try to summarize. So I was trying to arrive at this using these 2 points. So you can see that the number of ligands are 4 in tetrahedral and 6 in octahedral. So there's a 2/3 reduction. Approach of ligands is not along the axes and it accounts for 2/3 reduction. So it accounts for further 2/3 reduction. So what we obtain is delta T is in fact 4/9 times delta naught. Okay, delta T is 4/9 times delta naught. It is actually lesser than delta naught, and so it is so less that all ligands behave as weak field ligands. All ligands behave as weak field ligands because the repulsions are so less that irrespective of the nature of ligand, they will behave as weak field ligands. Okay, yeah, this is the mathematical. Okay, so way of representing it. There is another rigorous way, but for now this will do. That delta T is 4/9 times. So there is a 2/3 reduction accounted for this. There is a 2/3 reduction accounted for this. So 2/3 reduction accounted because of number of ligands. 2/3 reduction of splitting accounted for the approach, and so it becomes 2/3. So 4/9 times delta naught. Okay, and all ligands, there is no distinct. We will not have strong field ligand or weak field ligand. All ligands behave as weak field ligands when it comes to tetrahedral complexes. Okay, all ligands behave as weak field ligands so you can see this delta T is 4/9 delta naught. So it is because of 2 reasons. 4 ligands does not coincide with the direction. Okay, does not coincide with the direction. Is that clear? I hope you have understood this. Okay, Clear? I hope you have understood this. Chalo, very good. So, finally, what are the limitations of crystal field theory? हमने बहुत पढ़ लिया crystal field theory. What are the limitations of crystal field theory? So, limitation of crystal field theory is we consider that crystal field theory was developed by physicists to help chemists. So they considered the ligands as point charges. We didn't take into consideration the sizes of ligands, and so no steric effects can be explained. So this theory follows that the ligands are point charges. Also follows that the anionic ligand should exert greater splitting, because anionic ligands, so if they are considered charges, then if there is an anionic ligand and there is a ligand which is neutral, then anionic ligand should exert greater splitting, but that is not true. CO exerts greater splitting than Cl minus. So therefore we cannot say that how it does not explain this part very perfectly, that how neutral ligands, some neutral ligands function as a stronger field ligands compared to anionic ligands which function as weak field, or it does not take into account the covalent character. Okay. So the homework question for today, that will involve a bit of effort. You have to identify the angle between the ligands and dxy, dxz, just a moment, xz, dyz, and ligands and dx square minus y square dz square. So the angle between the ligands, I had just told you that in in tetrahedral complexes, the ligand have a smaller angle over here. So they have a smaller angle over here and they have a larger angle over here in a tetrahedral complex. Okay, in a tetrahedral complex. You have to tell in the comment section that what is this angle? What is the angle between the ligands and dxy or dxz or dyz, and ligands between ligands and dx square minus y square dz square in a tetrahedral complex. Okay, tetrahedral complex. So you have to give me the answer in the comment section only for tetrahedral complex, because I have said earlier that इनके बीच ligand and the non-axial d orbitals have a smaller angle, and ligands and axial d orbitals have a larger angle. Okay. Yes, ma'am. Sanjay Shukla, CFT takes into consideration only d orbitals. Yes, I and Paul sir both will teach on Catalysis channel. Yes, Tanishq. Okay, so with this we end today's session. I hope you have enjoyed crystal field theory thoroughly. From the next class, we will start with valence bond theory, and valence bond theory will try to understand the hybridization of the complexes. In valence bond theory, you will understand why we had taken, or what was the purpose of taking crystal field theory before valence bond theory, because to explain high spin, low spin, things become easier. Okay. Yeah, Sanjay Shukla, yes, that's a limitation, but since we are only concerned with the properties of metals which have d orbitals, that does not actually turn out as a limitation. You can say that we do not consider all the orbitals of a metal And if we do consider all the orbitals of a metal, then we have to go for a higher and more rigorous theory, which is known as the ligand field theory. Okay, so how was it found that the approach was not direct? Because in tetrahedral complexes, DS was in tetrahedral complexes. If you draw the approach of ligands and you draw the way the orbitals are present, you can yourself see that ligands are not approaching in the same direction as in which the orbitals are present. Okay, chalo. So bye bye guys, have a lovely time, and please do drop your answers in the comment section that what is this angle. Okay, so try to like show your work, that will be a lot better, so that I'll be able to understand that whether you have solved it by using geometry or by using trigonometry, and by using your complete intellect as like to whatever extent possible. Take it. Chaliye. Bye bye guys, have a lovely time, and let's meet in the next class. And the next class will be on valence bond theory.